Welcome to this presentation about multi-objective optimization of long-run average and total rewards. My name is Tim Quatmann and this is joint work with Joost Peter Cartoon. Okay, we are going to talk about multi-objective model checking of probabilistic systems. This is all about studying trade-offs between various objectives for our system. As a very high-level example, consider the way you can drive a car. You can drive as fast, as safe, or as cost-efficient as possible. But the fastest way to drive is most likely not the safest way to drive. So there is always some kind of trade-off, and we are about to analyze these trade-offs. For models, we consider Markov decision processes, or MDPs for short, which offer non-determinism and probabilistic branching. And we also consider Markov automata, or MA, which extend the notion of MDPs with an additional notion of continuous time in the form of Markovian transitions that work similar to continuous time Markov chains. And actually, that means that they model an exponentially distributed delay. We also attach rewards to either the states of our models, which are then collected over time, or to the transitions of our models. And here the interpretation is that once we take the transition, we collect this reward exactly once. For objectives, we consider expected total rewards, which intuitively sum up the rewards along the execution. And then there are expected long-run average rewards, which consider the average reward collected per time unit. Let's look at an example. We have this model, which is supposed to model a machine that's either in a working state, in a failed state, or in a repairing state. The states are connected via transitions. And we also have rewards in this model. We have two different reward assignments. First of all, we have this green thing, R1, which models the number of produced units for our machine. And we have R2, which models the maintenance cost. And as you can see, the maintenance cost is collected while we are staying in the repairing state, whereas produced units are produced in a working state. Good. So with that, we can already compute the expected maintenance costs per day of our machine. And this is turns out to be minus 0.11. And you can also compute the expected number of produced units per day, which is 88.9. And both of these are long-run average objectives. We can just plot these two numbers like this in a coordinate system. And this is then to visualize the trade-offs later. But first, let's make this model a bit more interesting. Let's say in the fail state, we have the opportunity to switch out some components, which then yields to a probabilistic choice between either going back to the initial configuration or choosing two different kinds of configurations, which then look very similar to the first configuration we had already. But they are different in the sense that, for example, here we produce more units per day, and but this also fails faster. All right, we can then, for each of these configurations, again compute the two measures I mentioned before, so the expected number of produced units and the expected maintenance cost, and draw these in this coordinated system. We already did that for the configuration number 1, and for configuration number 2, we would end up with this point, and for 3, we would get this point. Now, if we will let the system run, there are of course different strategies to switch the configurations, and in fact there are infinitely many. I could, for example, say I am in configuration 1 for 100 days, and then with probability a half, I switch, and then wherever I end up, I do something else. So there are many possibilities for strategies, and we cannot possibly evaluate all of these strategies. But what multi-objective model checking does for us, it provides this set called the set of achievable points, and the interpretation is that any strategy I can come up with will give me some point in this green area. There's no way to find a strategy where a point lies then outside of this green area. Let's make this a bit more formal. I consider objectives to be essentially random variables that map infinite executions to values, either real or minus or plus infinity. And as special cases, we consider total reward objectives, which just sum up the reward along the path. And we consider long-run average reward objectives, which takes the average reward per time of a path. then we have strategies which map finite executions or finite paths to the distribution of over actions that we should do after that execution. And this resolves all of the non-determinism in the model. So if we have a strategy, then the process becomes purely stochastic, and we can then compute the expected value of our random variables or of our objective f like this, and this then yields the expected value of f. Now we can define this green area. As I said, it's called a set of achievable points and defined like this. So for L objective f1 until fl, we say a point P is achievable if there is some strategy sigma such that if I evaluate sigma for each individual objectives, I end up with values that are greater or equal to the values given by the point P. So every point P is kind of achieved by some strategy sigma yielding these values. And yeah, the set of all such point P is denoted by h of phi. And our task in multi-objective model checking is to compute or at least approximate this set h of pi. So what we do in this contribution, we extended a sandwich algorithm for approximating this set. So this algorithm is generally used for convex multi-objective optimization. It has also already been applied to prosthetic model checking, in particular to MDPs with total rewards. But what we do here is we show that this algorithm can actually be applied in a more general context, in particular for Markov automata instead of just MDPs, but also for general combinations of objectives. So any kind of objectives that I can express with random variables, as I've shown on the previous slide. For any kind of objectives, I can use this algorithm. The only thing is that the algorithm kind of uses a black box that computes weighted sums of objectives, or at least it analyzes weighted sums of objectives. We will see that in a second. And if you want to use the algorithm for your special kind of objectives, you would need to somehow specify this black box. And we did precisely that for long run and average reward objectives, and also for mixtures of long run average and total reward objectives. And as we've seen at the end of this presentation, our approach empirically at least outperformed the existing approaches, which were all based on linear programming. All right, here's the sandwich algorithm. The rough idea is that it repeatedly selects weight vectors W, which have a non-negative entry for each objective. And then we compute strategies based on this weight vector, sigma W. And the strategy is supposed to maximize this expression. And this expression here essentially considers a weighted sum of the expected values of each individual objectives. So this thing here yields a point in the coordinate system, and then we take the dot product with the weight. So this is indeed a weighted sum. What does this strategy bring us? First of all, if we evaluate the strategy for the individual objectives, we end up in a point that's by definition achievable. That's good. But on the other side, we also have that any achievable point has to lie within this set, which essentially encodes a half space. Here the idea is that any achievable point, if I take the weighted sum of the point and the weight vector, then I end up with a value that is less than the weighted sum I would get with the strategy sigma W. And this essentially holds because sigma W maximizes, in fact, this weighted sum here. Good, let's give these two expressions a name, PW for the achievable point and HW for the half space. And for the different weight vectors we analyze, we essentially just collect these points at these half spaces. And doing that, we have the following invariant, which holds. And it says that the downward closure of the convex hull of all the points we collect is a subset of the achievable points, and the intersection of all the half spaces we collect is a superset of the achievable points. Let's draw this as an example. If we consider this weight vector first, W1, we will end up with some point PW1, for example, here, and the half space, which is indicated by this area below the dashed line. And we see that the point always lies on the half space, or on the boundary of the half space. And with our invariant, we get that any achievable point has to lie within the half space. So in particular, all points in the red area are not achievable, whereas every point in the green area is certainly achievable because this is the downward closure of PW1. We can continue with another weight vector and then fuse these results together from the two weight vectors, which will then end up with this red area here of points that is certainly not achievable, and this green area, which is the downward closure of the convex hull of these 2 points. So the downward closure of the line connecting these 2 points. And then we can continue with yet another weight vector and so on. And with doing that, we will further and further increase the green area and the red area, and therefore get a better and better approximation of the set of achievable points. We can stop this algorithm at any time when we think the approximation that we currently have is already sufficiently precise. Good. What is missing is how we compute this strategy sigma w. So this is the black box that I mentioned. We somehow have to find strategies that optimize these weighted sums. And if we only consider total reward objectives, this has already been solved. And here the idea has been to push this weighted sum from the expected value level all the way down to the reward assignment level. So what we get is that the weighted sum of the expected total rewards is actually the expected value of the sum of the rewards. And if we know that, we can essentially reduce this to a single objective model checking task, which basically says, okay, optimize this expected total reward. And this can be done with off-the-shelf algorithms for single objective model checking, such as value iteration, policy iteration, or linear programming. Now, if we only consider long-run average objectives, it turns out that we can do just the same. We can again push the weighted sum all the way down to the rewards, and then we use single objective methods to compute a strategy that optimizes this expected long-run average reward. So that's actually quite good. Now for mixtures of long-run average and total reward objectives, here we have we cannot reduce this to just this one single objective model checking query, but instead we have two single objective model checking queries. And the idea is basically to first analyze the weighted long-run average objectives. So only consider the long-run average part, and we do that on the maximal n components of the model. And a maximal n component intuitively is a strongly connected submodel that, at least under some strategy, can never be left. So for example, these are the n components of this transition system, of this Markov automaton. Good. And so what we do is we compute the we analyze each n component and get the long-run average value for each n component. And then we fuse these results together by basically collapsing each n component and replacing it with two states. Here, basically, the idea is that at each collapsed n component, we can decide whether we like this n component and collect the long-run average rewards, or whether we want to leave this n component again. Then we can fuse the results of the n components together and also incorporate the total rewards. And this will give us yet another single objective query, which then analyzes the weighted sum of the long-run averages and the total reward assignments. And here, in fact, we would get that we maximize this expression, and that would yield a strategy that says, okay, we have to stay in this first configuration. Okay, more details of this can be found in the paper. For now, I want to focus on the implementation that we did. We implemented the whole thing into Storm, and the implementation supports MDPs and Markov automata specified with Prism or Jani. We also support various multi-objective queries, including qualitative, quantitative, and Pareto queries. For the single objective long-run average computations, we employ value iteration, and for total rewards, we have sound value iteration. And we also indeed support time and step-bounded objectives, which have not been covered in this talk. We compared our implementation with the tool Multigain, which supports only long-run average reward objectives for MDPs, and does so via linear programming, and it uses the LP solver Gurobi to solve these linear programs. We have 10 case studies, each with 3 instances, so there are 12 concrete Markov automata and 18 concrete MDP models, and we have epsilon approximations of achievable points with epsilon set to 10 to the minus 4. All right, here are the results. So this is a scatter plot. Each point in this plot essentially says the runtime of Storm in the X value and the runtime of Multigain in the Y value. So the far more we get above this line, the better Storm is compared to Multigain. And in particular, we have timeouts and memory outs indicated here. And so that means at any point on these two horizontal lines means that Multigain ran out of resources, whereas Storm was able to process these. So you see that Storm is often several orders of magnitude faster and much more better with respect to scalability. And we see that Multigain is often stuck in solving all these P linear programs. So we conjecture that the speed up of Storm is not only due to an engineering effort, but actually also due to having the better approach, at least for these benchmarks. We also have some more experiments that are outlined in the paper. To summarize these experiments, we have there observed that Storm can handle millions of states and also up to 4 objectives. And we also observed that the runtimes are similar whether we consider a Markov automata or an MDP. So that doesn't make much of a difference with respect to runtime. And it's also similarly for if you only consider long and average objectives and mixtures, this always has similar with respect to runtime. So let's conclude. We have seen an anytime algorithm for approximating the set of achievable points. A nice asset of this algorithm is that it reuses or it allows to reuse single objective model checking techniques. So it's not entirely reinventing the wheel. The algorithm is applicable to all kinds of objectives, but in particular, we have seen this for long run average reward objectives and total rewards. Our implementation in Storm outperforms the existing approach based on linear programming. And for future work, we plan to incorporate partially observable models as well as stochastic games.